welcome Missy Cummings.
Thank you. Thank you for having me. So if you hear all of those titles after somebody's name, it means that I come from a small engineering school. And since I'm the head of robotics, and robotics touches all of those areas, it means, and of course, you know, I am also a rare female professor in this field, and all the departments want to point to me as, wow, we've got some of her. It also means I spend way too much time in meetings. Okay, so you heard a little bit about my past. It is true. Are there any Air Force related people in here? I always like to find that out because I like to say that I've landed on aircraft carriers, which is what makes me better than almost everyone else, especially Air Force people, since they can't do that. And so, but why that's relevant today, other than to let you know that I am really fun at parties and have lots of stories, but it also means that I was on the cusp of the technology change inside the Navy where I flew, the first plane I flew was an A4, which is all manual, and then I made the move to F-18s, which is a fly-by-wire plane. So I went from this place in my life where I was doing everything to babysitting a computer. And you know, not only is that just interesting from a historical perspective, but it actually frames where we are in the world right now. And in fact, when I was flying F-18s, I had a friend a month die. Someone I knew every month was dying in what would be considered then, and still today, a very advanced aircraft. And it was always pilot error, which is to say it was always a man-machine interaction. So I'm a rare academic who actually, I'm the picture of Dorian Gray. Only some of you are going to get that, meaning that I think I look younger than I actually am. I've had all of these lives, but my past lives really helped me formulate the reason why I have this lab called the Humans and Autonomy Laboratory, which also is a joke, but you have to be over 40 to get the joke. And so I'm not going to tell you what the joke is. I'm going to make all the young pups go find out why there's a joke in the name of my lab at Duke. So, you know, we hear a lot about cyberphysical systems, and it's funny because academia goes through fads, and whatever is trendy, you'll see show up in the names of things. I mean, artificial intelligence was trendy, then it became a bad phrase, then it was replaced by machine learning. Now it's being re-replaced by artificial intelligence because we have trendy fads. Cyberphysical systems is also a trendy name that just means there is some kind of computational system that interacts with the real world. We've had those ever since we've had some even very basic computers. I would say, even though I would say I'm in cyberphysical systems, which really anyone who's in engineering is somehow related to a cyberphysical system, a more specific name for what I do is called human supervisory control. And you see it on the slide. It's where you've got some person, in this case it's an Army enlisted man, no college training, who's actually trying to control this shadow drone. And he's not doing it directly. He's affecting control through a set of controls and getting some feedback through the displays, but actually a computer somewhere, either on the plane or some kind of cloud-based computers, closing the feedback loop on the other side. And so you basically got effectively 3 loops going on, feedback loops. You've got the one that's happening between the computer and the vehicle, between the human and maybe what's going on in the computer, and then globally the overall feedback loop. And so that's really where my research sits. It's looking at how can we effectively control and supervise this system, understanding that the human is in or on the loop somewhere. And I typically do a lot in safety critical systems, so transportation systems forms a big part, although not exclusively everything that I do. So this is an example of some work that I've done in the past. This is a mining robot. This is a dump truck. And so now in mining worlds, they're trying to replace as much equipment as possible with robots for obvious reasons. And, you know, how to get one person now to basically be an air traffic controller for multiple robots has been a problem that they've been having. And this is in Western Australia. But to give you a sense of size, it's hard to see, but my student is wearing the yellow jacket. You see him up in the far right. Look how tiny he is compared to that dump truck. That's how big the dump trucks are. They're huge. Not just transportation, though. I do a lot of work in process control, oil refining, nuclear power plants, because in all cases, humans are supervising a complex, automated, cyber-physical system, and then how to make sure that the humans can understanding that we seek information-rich environments, but we are also information-limited in how we make decisions, particularly under time pressure. So we work a lot in those spaces. I made my career, I got tenure at MIT for all of my work in drones. This is the Alaska oil pipeline being investigated by drones. So this is a new and upcoming emerging area. And so I actually work on the human control of drones, but we're also looking at now, my research has broadened out to looking at everyone else in the ecosystem. One of the biggest problems they're having with the oil pipeline right now are people shooting the pipeline. Why? See, I come from North Carolina. I know the answer to that. Why not? Why wouldn't you shoot the pipeline? People are bored, they have guns. We shoot things when we're bored, particularly in these remote environments. So, and it's obviously costly, and so using these drones to patrol the Alaska oil pipeline is critical, both from a safety perspective of preventing the oil spills, but also to make sure that, because it actually, getting people in the field is dangerous, getting them up to inspect those pipelines closely is dangerous, expensive, so it serves everyone's purpose. And then, of course, aircraft. I'm not even going to talk about it today. I have an entire program in flying cars going on right now at Duke. Don't hold your breath. You're not going to get a flying Uber anytime soon, despite what Uber is going to tell you. But there is a big move afoot of making passenger travel autonomous. You're never going to see a big plane like this be truly a drone. I mean, they're mostly a drone right now, but you'll always have a pilot on board. Mostly because you need people to control other people. But for small aircraft, it is coming one day. Probably, you will see, well, we've already seen people flying in these. Regular commercial service, if you're really rich, is in your near-term future, but not if you're really rich. Okay, so today, though, I'm really going to talk to you more about modeling. This is an academic crowd, and I thought, I'm going to move more into lecture mode than, trying to rally the crowd mode, because I think that most of you could benefit from thinking about how, when, why we should be modeling humans in these systems. Of course, my own students ask these questions, and so I present this list of questions. I'm happy to provide you with these slides later. But they're really this list of questions about why would I need an operator model? Pretty much once a week, I have someone from external to my university come to me and say, I need a model of a driver. I want to start doing some driverless car work. I do work a lot in the driverless car world, or self-driving car. And I need a model of a human driver so I know when to have the automation either come in and shadow the driver and take over when the driver is not paying attention, or I'm doing a fully automated mode and I need to bring the driver back in at the right time. So I need a good model for that. Sometimes we need models of pedestrians, because now driverless cars are moving around in the world, and we need to figure out what are the right models for people, pedestrians, bicyclists in the ecosystem around the car, drone pilots, and why, if it's not just trying to understand when to bring the person in, and that's actually what we call function allocation. When you want to hand control from an automated or autonomous system to a human, it's called the handoff problem, but it's also one we call function allocation. When, where, what are the right functions that a human should be doing by themselves? Which ones should automation be doing, or autonomy, and then what should they jointly be doing? So the bulk of my research is in that shared function allocation space, but that's also important because it helps us understand how to design better algorithms. It's not only when to hand over is an important question, but how much should you be handing over? Should we, Toyota basically has a guardian concept where the automation is shadowing you as you drive, and if you start to do something bad, theoretically the car takes over. I just rented a car where this happened for the first time, where it wanted to keep me in the lanes, and I wanted to not be in that lane, and I didn't even realize the car had this capability, and I could feel the struggle going on in the steering wheel. I really felt that somebody should have told me before I rented this car that, because I was really fighting, and I thought something was wrong and I was going to have to take the car back, and then I figured it out and just turned it off. All right, and ultimately what we want to do is we want to be able to design better systems, better decision support tools, even better interfaces. So for example, it took me forever to find that button in the car with this lane protection status, because I didn't, the icon, I had no idea. It had like a swervy road on it, so I thought that was the traction control button. How did I know that that was the actual self-driving mode? Okay, so if we have these models, are they context specific? Is a model of me in a Toyota the same as a model of me in a dump truck or in a minivan? And the answer is sometimes it is, sometimes it's not. But in fact, if we had better models of humans, we would understand just how generalizable they are, not just across cars, for example, but across modes of transportation. So we want to know how would I change a design? If I change something, if I have a new drone control station and I change one of the buttons, is that going to be a good thing or is that a bad thing? And can I know using an operator model that that might be a bad thing before I actually have to spend all the money getting a flight test certification, spending the money on human subject testing, going through an IRB, right? It's pretty costly in terms of time, resources, money to do human in the loop subject testing, and using models to answer some basic questions early on in the design process is preferable, especially if they're kind of yes, no questions. Should I do this? Should I not do this thing? We're working a lot for the military to look about chaining these functional models. So for example, if I have an interface where I'm flying a drone under one set of conditions, let's say I'm supervising waypoint to waypoint navigation, and then I get to my location and I want to switch into an inspection mode, for example, and I want to inspect that oil pipeline, can I have an operator model of the waypoint path planning and then link that to an operator model of actually the inspection, understanding that I need to link two models because they represent two different functions. One model would never cover both of those, but we're looking at how to chain the models in an effective way so that you can actually think, you could go, my dream is to create a library of operator models, and so that you could go to my website, pull down, oh, this is a person's model under X conditions, oh, and then I want to add this functionality, and then I could just drop that model in. Of course, how to do this in off-nominal conditions, this is another big problem. We can generate pretty good models on a normal, average, typical day, and then when things go wrong, it dramatically can change the human model because we have high variability in the way that we think and approach and solve problems. And then, of course, like I talked about, using them in design. Okay, so enough chit-chat. Let me just tell you about some of the models we've been creating and give you a perspective. All right, so this is a project that we've been doing for the Office of Naval Research. The idea is that you have an operator controlling multiple drones. In this case, you'll see the drones in the little blue upside-down U's. Targets are in the red triangles. Now, the job of this drone operator is to fly the drone to a target and then go into this little window right here, and it's a reconnaissance mission. The operator is supposed to count the number of intersections at a particular location, and that's their job. So they're trying to maximize getting to as many targets as they can and count all the road intersections correctly. Unfortunately, it's a malicious world out there, and somebody's trying to hack drones. It's actually relatively easy to hack a drone by today's world. It's a GPS spoofing. It's easy to hack anything that has a GPS signal. And in fact, the military has lost a super secret drone because it was GPS spoofed. And so now we're trying to figure out ways to maybe help the operator, help the automation know that it's been spoofed. And we can do that because the GPS signals that send the drone wherever, that's independent of the video imagery that's coming down from the downward facing camera. So you can actually see the ground below you in what would be the reconnaissance camera, and that is actually independent and not at all related to the signal on the GPS. And so the idea is, if the operator thinks that they might be under a hacking attack, can they actually visually correlate where the map tells them they are? Because that's what would happen. If you're GPS spoofed, your position on the map will be where you think it should be, but it's actually somewhere else. And we're trying to see how well people can correlate the image that's coming out from the video camera from the map imagery, right? So these are in theory, they would marry up. But it's actually information dense. It's hard to see. So let me show you a video of how this looks, what this looks like. By the way, we developed this software using the Office of Naval Research, which means that it's freely available to you. It's a great test bed. It was built with CitySim. So the map underneath is like a generic world, which we needed when we start to do human subject trials, so that we have a world that no one is familiar with, so that there's no inherent bias anywhere. And so you can see that the person is clicking and they're counting the roads, and that's actually very similar to what an actual military camera would look like if you were doing these kinds of missions. And then, you know, he's doing some path planning. We actually have a suboptimal path planner in here intentionally because we're trying to see if people recognize that there are better routes and paths to plan. The yellow are hostile areas. They kind of pop up. They're dynamic threats that eventually come and get you. Did we see the hacking event yet? Did it come up? All right, eventually there's a hacking event, and you'll be told that there's a possibility that you're hacked and that you need to go into that mode. And then you go into a matching mode, and I won't show you this in the interest of time, but if you want to see more, again, I can give you the game. You could download it today and play it yourself. So we wanted to know, first of all, oops, we skipped a, no, that's right. First of all, we wanted to understand how people were prosecuting the hacking. What were their strategies? We did not train them at all. This capability does not exist in the real world. The military does not use this. So we really had no clue about what is the right strategy that we should be training people to. So we ran an experiment with, I think, about 40 people, and we let the strategies, we wanted to see how people would adapt to this world. So how do we do that? So in my lab, we like to use a hidden Markov model technique. I'm not going to go into the details of this, but basically it's a way that you take observable states. In this case, you'll see this table over here. It's all the places that a person could click on an interface. So it's an actionable state. It is 100%. We know that human both saw and tried to understand when they clicked on a state that was definitely taking an action. And then we develop a hidden Markov model, we train the model, and then we determine the transition and emission probabilities. The transition probabilities are represented there between, the likelihood that you would go from these hidden states, right? So basically, when you do a hidden Markov model, you take all the observable states, and then it's an unsupervised learning technique that it basically clusters the states to show you how people, however they did, emerged into own specific clusters. And then so what you see is, even though we had 10 observables, they get clustered in about 6 states, 6 hidden states. And when we call these hidden, because we call them cognitive states. They're cognitive groupings, clusters of behaviors that we see that co-occur with each other, and they actually tell us a lot. So for every hacking event, every person had 4 hacking events through all their trials. And so there were 40 people, each did 280, so 320 hacking events. So from that, and understood this is low data, so we can argue about that later. From that, we developed this hidden Markov model. And what we can see is, we understand that they start by perceiving hacking, they're notified, and you can actually see for each of those events, you can see what emission probabilities match to each of the hidden states. And then, it's an eye chart to read, but what's important to know about this is when you look at the dominant strategies, we can actually see 2 strategies emerge. We see that some people, when they start, they go and they adjust a waypoint. And then once they adjust a waypoint, they make a decision and they end. And we know when they start and end because there's a start and an end button. So what these people are doing is they decide that they're going to introduce a waypoint, like say the UAV is traveling from here to here. They introduce a waypoint here and they cause a turn. And then and what they're looking for is they're looking for the motion as the vehicle starts to make that initial turn to go to the waypoint. They're tracking to see if the ground turn, what they see in the little camera matches what they should be seeing on the map. And then they make a decision. The second dominant strategy that we saw is, some people don't think that way. Some people actually look to see where the vehicle is going, And instead of adjusting a waypoint, they actually change the target. So they're doing the same. They're basically getting a heading change, and then they go and select the UAV, and then what they're doing is they're waiting. They're actually using the landmarks. They're not using the motion so much. They're actually driving it to a specific landmark, maybe in an unusual building. We had some circular buildings in there to see if people were attracted to that as a visual reference. We actually had intersections, and we had land-sea transitions. It turns out that most people anchored on the special road intersection, something funky, something like 5 roads coming in, maybe a Y intersection, and that tend to be people's favorites. But the difference in these two strategies are, one group was anchored on the initial motion, the other one was actually anchored on the very specific spatial point on the map and whether they could correlate it with something unusual. Now, it didn't really matter performance-wise for most people. Overall, we saw no difference in the strategies in terms of performance. Was there a question?
Yeah. Mm-hmm. So when you say these two groups of people, are you using a single HMM and trying to figure out that these two groups of people from the Viterbi decoding, or are you actually have like a mixture of HMM?
Yeah, so let me go back to that. So it's not two groups of peoples. We're just saying these two strategies. We actually went back and then classified which groups of, like a k-means clustering or some other just basic clustering, just to see who fell in what strategy. And it turned out, not surprisingly, there were groups of people, the target strategy, the waypoint strategy, and then there were some that were target dominant but still used waypoint, some that were waypoint dominant still used target. So there were really 4 clusters of people. It didn't really matter. Neither strategy was dominant, at least when we looked at everyone. So then we said, well, there was something interesting in the statistical results that came out. It turned out that of the 40 people, 2 had 100% performance on the hacking. So they were the only ones. Our 2 people that performed flawlessly also, not surprisingly, had daily gaming experience. And they were the only ones that had they were daily gamers. And so then we said, aha, okay, well, let's look and see if we had 2 people that performed perfectly. Let's see what their strategies are. So we call these the master participants. And so we looked at the strategy for our one of the best performers. And not surprisingly, he was the very direct strategy. Okay, we're like onto something, because what we want is to know what the best strategy is, right? We don't know. The Navy doesn't know. Nobody knows what the best strategy is. Of course, as an engineer, what I want is the one best strategy. And then we could train people to it and potentially design the interface to that. And yay, big victory. So what do you think the second person did? Our second master, because humans here just exist to frustrate your research. The second person not only did the second strategy, but also he was one of the mixed. He was kind of target dominant, but every now and then would put in a new waypoint. Now the difference was the second participant took longer to make their decisions than the first participant, who was on the shorter strategy by a long shot, which makes sense. But in the end, neither of them was superior. So, this is, by the way, this is real research. I'm kind of telling you all my dirty secrets. Dan?
How sensitive would the mastery have been to your change of criteria in the task?
Well, so that's a good question, and that leads me in. So that's where we're headed next, right? So now that we actually understand that these two strategies exist, the next step in this research is this tool right now, the HMM, is diagnostic. It's post hoc. But now we're going to turn it into a predictive tool, and we're going to start using it in real time to start making, suggesting a piece of a strategy for a person. So we're going to track each participant, and they will get training, specific training this time, and we'll see if they start to fall off of a strategy and the automation gives them a recommendation to come back onto a strategy if their performance actually improves.
Do you worry that there are lots of tasks where your criteria, where the task itself is complicated enough that you could imagine totally plausible criteria, and nevertheless you'd have very, very different performance metrics against one and the other?
And that is yet more research, right? Now, we've actually done this HMM strategy on a very similar interface, almost the exact same interface, but did not have the hacking. And we actually did see very similar strategies, at least in the navigation and waypoints. So this is, of course, where replication and making experimentally in formal settings, making tweaks and then measuring, right? So yes, that is definitely, in my poor PhD student, he hears me give this talk and he just sees his graduation date going further and further away. All right, now, on that same note, let me show you about a similar approach, but using a different interface so that Dan can get an appreciation for what these look like. So this is a project that we're working on with NASA JPL. We're working with the Mars rovers teams. So there is a problem where the automation that gets embedded, Mars rovers have automated path planners on them. The operators don't use them. They insist on hand driving all the robots on Mars. Why? Because they don't trust their own technology, right? They still feel like that must be a human in the loop really driving at every point. And I've written a paper about this if you want to go read it on the website, but it's costing the science. It costs them tangible results by having the humans insist on basically manipulating this thing every inch across Mars. If they would use the automation, if they would trust it more, then they would probably have better science outcomes. And so this effort, which is sponsored by both JPL and ONR, is trying to get at what is causing trust. Can we promote trust? Can we even, what does it take to measure trust, and what does it take to potentially improve on trust? So one of the things we did, this is a very simple path planner that takes you from the black dot to the white triangle. You have to navigate these obstacles. In this generic setting, we made it be a submarine where the submarine has to surface a few times across the interface to basically get ground truth. So in real life, when you surface a UUV, unmanned underwater vehicle, you actually get a GPS signal that tells you exactly where you are. So you can get real-time updates for ground truth as you're going across the screen. Up at the top, we have something called a risk budget. This was one of our ideas, that if you actually give people a risk budget, a tangible risk budget, and they can see how much risk they use at every interval, maybe that will give them a better sense of trust and confidence. And then on the control panel, we're actually letting people access the step size that is underpinning the algorithm. And we've tested this with a couple of different algorithms. And in fact, we've designed this, you can have this one too. We've designed this so that you can plug in your own algorithm and run your own test for whatever reason you would like. So people can take small, medium, large steps, and that generates to, I forget, whatever, 4 time steps, 6 time steps, 8 time steps, something like that. And then low risk, medium risk, high risk. That's basically how willing you are to get close to the obstacles, right? Because some path planners want to hug obstacles. Some path planners want to put you right in the middle, and it allows you to adjust with that level of risk. So just a real quick, if you want to see it in motion. And we're asking people all the time what their levels of risk are. They are asked to evaluate ahead of time what the risk will be, not risky, kind of risky, really risky, and for whatever reason the movie is kind of stuck. There it goes. So this person thinks this is kind of risky, and then they get to select what it is that they, and we're tracking this, by the way, we're tracking every click that they make on the interface. What they're doing is that they're exploring, they're doing a what-if analysis. They can click around and see their current solution with the proposed, what the last solution is based versus the current. We ask them about their trust and confidence. Now, conceptually, what we're trying to do is something called close the gulf of execution. So this is the 7 stages of action where you perceive, interpret, evaluate a plan, measure it against your goals, then you form an intention, and then you execute that action. And this is basically a well-known information processing cognitive loop of humans. And the gulf of execution is trying to close what you intended, how you evaluated it and set a set of goals, and then you formed an intention. We want to close that gulf, it's a known problem with interfaces that people have an intent that theoretically should match a set of goals, but there's often a gulf in particularly if interfaces don't give you enough information. So that's what we were doing. It turned out that in trying to close the gulf of execution, the only intervention that really helped was the controllability aspect. And it really only helped them stay within, they had a surfacing budget that goes across the screen, right? So the controllability, giving people a step size, by help, we mean it really helped them have better performance. It helped a little bit with their trust, the observability, putting the risk bar up there, that didn't help at all. Now, did it really help at all? It just wasn't a measurable effect. We didn't see it in this population. But in a crazy off way, it turned out we found something, this is very typical of human-in-the-loop data. So when we recruited, these were 80 people, by the way, which is a lot for one of these experiments. When we recruited the people, it just turned out that almost half self-selected to be women and half self-selected to be men. We didn't try to make that, and this is the way some experiments go. So we got half women, half men. When that happens in one of these experiments, because there has been research that shows that there is a measurable effect of genders and how they reason differently, we had to set it up as another factor unexpectedly. And we also saw, again, that video gaming thing showed up as significantly influencing confidence. But then, so we were asked this question, all right, so the men and women did not perform any differently. So neither of the genders was superior in solving the problem. But what we did see, there was a big difference in confidence and a small difference in how the two genders trusted the technologies. So we did that HMM thing again. So I put my clever students on it. I said, okay, here are how we mapped. These are the observables, buttons 1 through 9. And then I had them map on to models. One is male and one is female. I'm not telling you which one is which because I love asking this question in a group. Okay, so you're seeing everything starts with the execute button because they had to do multiple plans. So they would plan, they would go from 3 to 5 to 1 to whatever. Then they would hit execute, then they would do it again, hit execute, then they would do it again. And so you're actually seeing that you're seeing the predominant, on the right side, 51% of people would move from the execute button to the high risk long step. Okay, so you can see that. So which one is women and which one is, okay, who thinks that this is the female model? Raise your hand. Don't be shy. Be real. I mean, then you're not going to get in trouble. Female model, okay. Male model. Okay, so I'm sorry. Female. Who thinks this is the female model? Okay, so for those of you who are willing to at least hedge a guess, first of all, I throw you out chocolate for being brave, and you're wrong. You're wrong. You were all wrong. This is the male model, and this is the female model. And by the way, I've given this talk several times. I don't know. It's funny because almost always the majority of the group thinks this is the female model. Who would like to be super brave and tell me why they think that?
You just spoke about confidence, and we all assume women were less confident, and so clicking around more before executing, and this model's looking.
Yep, that's right. It turns out it's exactly not that way. So the women were actually much more efficient in their strategy, and the men were much more exploratory. Now, and that's the thing. So now we don't know what to make of it. These are, by the way, these are brand new results. This is just a few weeks old, and now we're trying to reform what we're thinking. We didn't set up the experiment to show that there's a difference in genders. That was never part of the plan. Now we see it, and actually going back into Lit Review, it does turn out that there is a big difference between men and women in other areas of psychology of exploration. So it turns out men will explore decision spaces differently than women. So now we are going to set up an experiment to test just that. And, so we're not really, the exploration isn't as much important as it is confidence and trust, because we want to know, are women naturally just very distrustful about technology and not confident, or is there something about promoting exploration that builds confidence? Dan?
In the good old days, if this were an ergonomic study of buttons and control panels, there would be a parameter space that you could formally explore and test robustness against interface design. I wonder if there is such a thing in game interface design. Is there a standard parameter space to express the many different interfaces? And if there is, how robust do you guess these results would be against perturbations in that parameter?
So, I mean, the answer is you could do simulations to try to get at that answer, and we occasionally will do simulations thinking that we have a good underlying model of the person, but that's what it requires, is to have a good underlying model to get at basically the design of experiments that you're talking about. If you were having to run it with real people, would be prohibitively, I mean, they're just, not that you couldn't do it, but these would be one of those longitudinal studies that would take a long time.
I guess the question is, you have this markup model, which is a wonderful, in some sense, low-dimensional representation. It's a great model, right? How stable is it against, even small perturbations, much less large perturbations?
Well, that's one of the things that we're trying to do, right? And that's why I'm trying to run as many experiments. And of course, the video game data, there is a balance. If you have too much data, then your model is too generalizable. It's not specific enough. And we've had those cases, as opposed to what are you trying to capture in your underlying population? Where do you actually see the differences? Now, I'm running out of time because I'm just talking too long. And I skipped over, let me come back to that, because we're going to talk about why and when do we care about thinking about humans, your individual variability as humans, and I'm going to come back to now to talk about, so this is the HMM modeling is something that I'm working on now, again, trying to get to this idea of building libraries with lots of data to really get at these issues of specificity, generalizability, modularity. In concert with that, my next big future thrust, and what we're just now kicking off at Duke, is this idea of explainable AI. And it's a phrase that sadly has gotten overused, just like AI has gotten overused. And so I'm trying to introduce now, I'm interested in explainable AI, but really more in the sense of justifiable AI. And I'm gonna tell you what that means a little bit more, because it really comes back to certification of AI. Like, how do we know that the AI that we're building, whether it's for a transportation system or any kind of cyberphysical system, is going to give us any kind of safety guarantee? And by that, I don't mean the guarantees of optimality, which many of you in the room are doing. That's great for you. Guarantees of optimality is a great academic parlor trick, but in the real world, you cannot say, and if I read one more article that says, oh, I can show you mathematically how I can guarantee optimality, that has nothing to do with how you guarantee safety in the real world. Okay, so here's a couple of examples of AI gone wrong that should be reminders of you to be careful, right? So Tay, who knows about the Tay bot from Microsoft, right? Hilarious, 16 hours. One of the early tweets from Tay. Here's a question, humans. Why is it National Puppy Day every day, right? That was in the early stages of Tay. And then after interacting with humans, which I got to tell you, the whole Tay experiment, really to me, the fascinating thing is how fast humans figured out how to screw with it, right? That to me, that was fantastic. I actually love the counter technology that people just like in this room do. Because within 16 hours, they had turned the puppy-loving bot into a racist, Hitler-loving, entity. And you're like, how did that happen? And how did the programmers not realize that this was going to happen? So then to kind of get at what one of my own students was thinking, I had them do, there's this data set, it's a very big data set of that predicts it's the variables are to help you predict whether or not a person is going to leave a job, they're going to quit after 7 years. And because this is, retention, people in Silicon Valley really, this matters how you're going to develop your retention packages. And so these are the features that we used to predict of a couple different models, logistic regression, neural net. And so the idea is that the factors in green are the ones that accounted for the bulk of the variability in the data, and the ones that are red are definitely not in the model, right? And you can see the percentages at which the prediction was made. And so this was an important example. So I asked my student, okay, so what's the accuracy? Guess what? The accuracy of these were virtually identical. It was off by 0.3% or something, but virtually 94.7 and 95% accurate, okay? So fundamentally, these two models are the same in accuracy, but they actually tell you two different things, okay? One is a very low-level AI technique, and one is a more advanced technique. So which one should you believe? And the question is, if you're a CEO and you were to believe either of the models, the ramifications to the money that you would spend for your HR programs would be vastly different. So should you spend money on reducing work accidents and reducing number of projects and increasing satisfaction, or should you increase their salary and then look at work accidents? Very different.
Assuming they're both very accurate, doesn't that just mean there's some dependence between the features here?
Maybe, but I mean, which one, how do you tell that to a CEO? How do you explain that? You have to give, based on this data, you have to give a recommendation for the CEO of what he should do.
I would bet that both, I mean, certainly the logistic regression could look at the null space of the objective function, for instance, and try to, evaluate that.
Yeah, but it's not obvious, right? And a lot of money is on the line, and if you make that recommendation wrong, you're going to be fired, right? So I think that this brings up the question of well, then how would we explain some of these interdependencies to people who are not experts in the field so that you can both do due diligence, but also try to make something actionable. And if we have time, I'll come back to that. And that really comes to this idea of, human judgment and bias are everywhere. So when I have my students develop any kind of machine learning algorithm, the idea first you have to do is what algorithm do I pick? Should I pick, and that was the study that we didn't have time to go into. We were doing some decision tree models for looking at how pedestrians make decisions about crossing or not crossing in front of a driverless car. But should I pick a fast and frugal tree? Should I pick some other cart type of algorithm, evolutionary tree algorithm? I don't know. Which one should I pick? Mostly people pick, particularly when they're in industry, they pick the ones that they used in school. And those ones, by the way, were the ones that their advisors liked the best, that knew the best, right? So there's this huge bias that we institute in U.S. students and that carries on. Then, there's actually, how do you even set certain parameters? Depending on the technique that you're using, some of the parameters that you have to choose, you choose where to initialize parameters. Why do you choose the way that you choose? Why not choose something else? We've been, in the HMM models, we've been looking at, what if you basically do an informed initialization for the Baum-Welch algorithm? What if you don't? What if you use a randomized? What if you use a uniform? How would the results change? And how different would the models come if you made different choices? And sometimes they can be very different. Sometimes they're the same, sometimes they're different. I don't really have the answer for you on that right now because we're working on it, but just your choice, your bias that you introduced in the development of this algorithm could have a dramatic effect. And then where do you choose certain thresholds for what you believe is accurate, not accurate, right? So these are all the biases that come in when you engage in an algorithm. Then in industry, it's not even clear who's interpreting it. In academia, my students develop the algorithm and then they interpret it. But that's not actually true in industry. Often some algorithms will get developed, they'll be passed on to somebody else in a company, particularly in the driverless car company, and then someone else has to do the interpretation. Not everyone interprets. This discussion that we're having over the logistic regression versus the neural net, I have my opinion, you might have your opinion, we might debate over the basics. But again, if you're not actually part of that discussion, the person who created the algorithm, it's not really clear how that can be communicated later on down the line. And then what should a sensitivity analysis look like? How much should you be doing? What kind of sensitivity analysis should you be doing? And that's just for the creation of the algorithm and the interpretation. This is a picture of a computer vision system on a driverless car. And you can see in this case, it's figured out, it thinks that there are 2 cars and 3 bicycles. That's what it thinks is happening in the world, right? And can everybody see that the bicycles are actually just an applique on the back of the car? There's not actually 3 bicycles in that picture. It's just a picture of bicycles on the side of a car. But yet that's not what the algorithm sees. So is this algorithm mature? Is this algorithm ready to go in a driverless car world on the real streets? I would argue that it is not. But then again, I'm not the one that makes the decision. The person who makes the decision is this person from, let's say, NHTSA or some other regulatory agency. So the other question is, How can you take somebody who has no knowledge, no understanding of the world? How would they start to understand what the weaknesses are? What should we be communicating? What tests should we be running? What should we be setting as thresholds, parameters? Should we let companies self-certify? So this is part of a larger conversation that's happening actually right now. In the House of Representatives and the Senate, they're arguing, there is a very hot debate going on right now about whether or not we should have standards for driverless cars on the roads. Now, we don't have enough time to get in there, but I will suggest one thing that I'm working on is, okay, there is no way that we're ever going to certify every single algorithm that comes out. Whatever assumptions you're making, whether it's how you initialize your parameters, the interpretation of your parameters, for very complex systems like driverless cars, there is no way that we'll ever be able to individually certify each one of those elements because it's a very complex system. So should we be trying to do that? So that's one argument. I stepped back and said, you know what, how do we certify humans? For example, pilots of aircraft they're autonomous agents. They're working with a lot of technology under the hood. How do we actually certify them? When you fly on a 737, how do you know that your pilot is safe? Well, you know your pilot is safe theoretically because the FAA does three things. It basically tests that their senses are correct, right? They have certain vision. For commercial airline pilots, they basically have to certify twice a year that they're not going to have a heart attack. So the bar is pretty high for commercial pilots. Then they have to demonstrate that they have adequate knowledge of the rules of the system. So it's kind of like a test where you get tested on the rules of the road. But then they actually have an in-flight test where you sit with an examiner, and the examiner focuses not on how you do routine operations, but how you actually perform when you lose an engine, when you lose communications. So all commercial check rides are basically hinge upon what do you do in off-nominal situations when things go wrong, right? So I think that there's a lot to be learned from that when we start to certify complex systems. People need to back off of trying to say, I need to certify that an algorithm is 99.999% successful. Because you can do that maybe in isolation, but then how that algorithm works inside the broader system that's far more complex. I don't think we can get there. But what I think we do need to start thinking about is how then to develop these systems levels check rides, if you will. It's not exactly the same, but how can we develop a set of tests, a series of tests, test when software changes, for example, that kind of gets at this same idea of the sensors must be good and must be reliably good. You must be able to sense the world around you. You need to have the knowledge to operate in that world. I think that's probably the easiest for autonomous vehicles, cars, planes to do. But then how do you act under uncertainty? All right, so with that, I'm sorry.
One issue about these AI systems, and I would characterize is that they don't generalize very well. But now if you're advocating that you're going to have a certain battery of tests, then what's going to happen is that the engineers will design to the test, will be able to pass the test, but then will not generalize to kind of unknowns.
Agreed. And by the way, every time I pick up the newspaper and VW does something bad, I think exactly that question, right? So VW, everybody know about the diesel test, that they both rigged the diesel test, for emissions. Then they also recently rigged the monkey, test with smelling the diesel fuel. So yeah, obviously bad actors are out there. And so I didn't say I had this problem. I just said I'm just now, trying to think about how we would solve that. So, but how do we solve that for humans? So pilots, what they do is after a check ride, pilots go to the bar and they all get together. And what do you think they do? What do students do before a big test? What do they do? Students go and find other students who took that test from that professor, and then they try to get all the answers they can about what is that, do you have an old test? What did that professor ask, right? So you're basically trying to get the intel about a test. Pilots do that too. So pilots have a sense of what the check rides are going to be like, right? We know, every pilot knows that they're going to have an engine pulled, right? They're going to lose an engine in flight, right? But just because you know that you're going to lose an engine in flight, you know, FAA examiners are very clever. They know how to put multiple emergencies together. They know how to change things up just so, right? So this is the other problem. Yes, it could not be a static set of tests because people would game the system. And this is actually where humans are even more important. Then how could you change it up? How could you introduce new elements, dynamic elements, multiple emergencies? What would the extent of that be? And also the software is changing, right? The hardware is changing. You would also have to take that into consideration, that you had multiple changes happening inside of a system. So yeah, it's just like a professor. You know, how do we stop students from getting hundreds on the test? We have to keep changing the test.
So even, ignoring cheating, right? I think that humans have we intuitively are very good at developing tests that sort of span the set of, that cover the basics, right? That cover sort of a span set of both capabilities and corner cases that we need to certify that somebody is proficient. You thought at all about, a sort of formal way of developing that kind of span set?
Yeah, so we're trying to get I'm trying to get an effort off the ground right now to actually work in that area. And the first place that we're looking at are computer vision tests, right? So, and I'm working with Senators Blumenthal and Nelson in DC on trying to think about, look, what we need is a computer vision test, right? We need to, and this would be true across all autonomous systems, because no question the long pole in the tent for these transportation systems are the vision systems, right? If perception works, then everything else, I think, we have a lot better chance of keeping the variance much more stable. So how to do a computer vision test. What would that look like? I kind of envision it as a two-stage test. I envision it like there's a series of images that would have to be constantly updated because of this cheating thing, or designing to the test. I could imagine, let's say Waymo wants to put their cars out on the road, then that means NHTSA would have to design first a series of quick tests, like, and I didn't even get a chance to show you, but there's a group of researchers out in Berkeley and University of Washington who showed that if you put 4 black and white stickers on a stop sign and you knew what kind of algorithm that was underpinning in the driverless car, you could trick that car into thinking that it was a 45 mile per hour stop sign, speed limit sign, right? So the question is, but actually just all computer vision systems, long shadows late in the day when the sun is going down that cause long shadows across signs, that's enough to confuse a lot of computer vision systems. So could you do like a 5,000 picture test really fast, in the computer head, show. You could probably get that done in about 20 minutes, and then you would at least have an idea, if the computer saw this, would it have seen the correct thing, right? So that would be a initial layer test. Then I think a later set of tests would need to come, and there are places who are doing this right now. Virginia Tech, for example, has a smart road system where you can actually put cars on roads, and then that would be a dynamic test. So I do see, at least for perception systems in the near term, we should have a static dynamic set of tests that would be very helpful. Now, but they would also need to change and upgrade. And once computer vision systems get more mature, and they eventually will. The question is not if, but in my mind, but really when and how much more development we're going to need. Then those tests would actually maybe need to change and potentially even go away, right? But to some degree, but this idea of having to keep up with how well the sensors are sensing the world, I think it is based. We think about humans. When you're a teenager, your sensors, when you get your driver test, we're not testing your sensors. Your sensors work really well when you're a teenager. We're actually basically doing the system uncertainty test. Can you actually execute? As you get older, your sensors start to fail, right? So that's kind of the issue that we need to think about. How do we keep track of sensor failure? What is the impact of software changes on sensor capabilities? And, how can we do this low-cost testing in a way that would not prevent innovation, but still guarantee public safety? And I think that's probably all the time we have.
Just about. Do you have any more?
Nope, that's it.
Maybe one burning question?